Welcome to clickmyprojects.com. Here we discuss about the LUT-SR family of uniform random number generators for FPGA architecture. Field programmable gate arrays are used in Monte Carlo applications because of their highly parallel nature of these applications and because it is possible to take advantages of hardware features to create very efficient random number generators. In particular, uniform random bits are extremely cheap to generate in a FPGA as large numbers of bits can be generated per cycle at high clock rates using lookup tables or FIFOs. In addition, these generators can be customized to meet the exact requirements of the applications both in terms of the number of bits required per cycle and the FPGA architecture of the target on platform. While it is possible to construct all possible generators ahead of time, the resulting set of codes would require many megabytes and be difficult to integrate into existing tools and design flows. In this paper, it states that a family of generators which makes it easier to use FPGA optimization generators by providing a simple method for engineering to instantiate an random number generators that meets the specific needs of their applications. Specifically, it shows how to create a family of generators called lookup table S random number generators which use LUTs as shift registers to achieve high quality and long period while requiring very few resources. The main contributions of this paper are LUT based shift register is a type of FPGA random number generators with period of 2 power 10,024 minus 1 using 2 LUTs and flip-flops per generated random bits. In this paper, the shift registers are in different sizes to generate the random number generators for long periods of time. Here, the feedback bits are loaded to different sized shift registers to provide a perfect long-term random number generations. This is our flow diagram. In the first stage, we give the input bits. At initial stage, we give the input as 0. Because of it is in reset condition at the initial stage. Then we instruct these bits to each shift registers in different sizes. In this, the shifting was made by for each and every clock periods. This shifting may also make the delay operations of each and every bits to load the input bits to operation area. In the operating side, we extract the XOR operations to provide the different sizes of random numbers, which can be made by interchanging the each and every bits to other registers. This XOR operation was finished and after we load these bits to and parallel registers. These parallel registers may also give the feedback bits to initial conditions. These feedback bits also load in the input different sized shift registers. Finally, from the parallel register, we extract the random bits. These bits may occur for up to 2000. Now I am going to explain running procedure of our project. In the first stage, we implement the designs by selecting implementation option. After that, we can check the syntax error by running check syntax. In the console window, it will display the any errors and warning details of our project. During this condition, it will generate the report files in the present folder. Then we can run the RTL schematic by running view RTL schematic. Here, this will display the total numbers of logical operations which are made in the internal codings. Now, click Add button and click Create Schematic. This is our overall schematic diagram. The input pins are clock, enable and reset. Here, at the initial stage, we reset the given input, and afterwards, for each and every clock periods, we can generate the clock and generate random numbers in the SR output register. So here the output pins SR out contain 16-bit. Thus we generate the 16-bit random numbers. Now we can view the technology schematic by running view technology schematic. Now click add and click create schematic. This is the internal view of technology schematic, which contains LUTs and flip-flop combinations. After, now we can run the timing diagrams of the simulation output by selecting the options simulation. Now select the main function and run behavioral check syntax. This checking the schematic view errors and warnings details. Now run simulate behavioral model. This will provide the guide window for timing diagrams for inputs and outputs details. This is our guide window of the timing diagram. Here in this, the capital I representing input pins and IO represent the inputs and output register. Here the SR out is the output register made as here inputs and output bus, and remainings are signals which contains the connectivity of internal ranges. Now I give the input for clock reset and enable. For giving input, just right click it and click force constant. In the force to value text box, I just provide 0. Now I give the reset input as 1. Give the enable as 1. Because at the initial stage, we reset the total overall chip. Now run by clicking the button run for the time specified on the toolbar. Now I just gives the clock period as 1. Now run it. This is the one clock period cycle, which is the negative and positive edge of clock frequency. So the one clock cycle representing 1, 0 and 1. After that, I giving the input as 0 clock. Now change the reset condition set to 0. Run it, and I change the clock frequency as positive edge. So for each and every clock period at positive range, it will set to shift register changes. So for each and every clock period, that means for one cycle of 0 and 1, our random numbers will be generated in the SR out variable. So for each and every clock cycles, random numbers will be generated at the SR out variable. This is our overall cycles. These iterations will be go for few stages. Thank you.